Hello everyone, and welcome to a couple of examples of conservation of momentum. And these are actually ones that we did last year, but I just thought I'd go through them again quickly with you so that you can see them before you try to do the packet. So here's example one. You've got a man of 70 kilograms and a boy of mass 35 kilograms standing together on a smooth ice surface. It's ice so that we don't have to worry about friction, and therefore there are no external forces. They push each other apart, so the man moves away with a speed of 0.30 meters per second. What is the final velocity of the boy? I don't know why they scream, but they do. So, we could do this problem mathematically, but I am going to try to do this with momentum bar graphs. And if you remember those are horizontal because we need to have a positive side and a negative side, since momentum, after all, is a vector quantity. If we make our system the man and the boy, then it is an isolated closed system, and therefore we know momentum will be conserved. So, initially, the man has a mass of 70 kilograms and no velocity, and since momentum is mass times velocity, he therefore has no momentum. The boy, who has a mass of 35 kilograms, also has no velocity, and therefore also has no momentum. So the initial momentum of the man-boy system is 0. After the explosion, after they push each other apart, the man, who still has a mass of 70 kilograms, now has a speed of 0.30 meters per second. Now we need to turn this into a velocity. So since in the diagram he went to the left, I'm going to call this a negative 0.30 meters per second. Multiply the mass and the velocity, and you get a negative amount of momentum of negative 21 kilogram meters per second. The boy, who still has a mass of 35 kilograms, has an unknown velocity. However, we actually already know his momentum. In order for the final momentum to be equal to the initial momentum, the final momentum's got to be exactly the same size, but opposite. Now we could just take that positive 21 kilogram meter per second momentum and divide by his mass and get the velocity. But I want to show you the equations as well. Momentum conservation is initial momentum equals final momentum. There is no initial momentum, as both man and boy are at rest. The final momentum would simply be the sum of the momentum of the man and the final momentum of the boy. Since we're trying to find the final velocity of the boy, we will solve for his final momentum, which would be equal to the negative of the man's final momentum. Each one of those are, of course, mass times velocity. So we have the mass of the boy times the final velocity of the boy equals the negative of the mass of the man times the final velocity of the man. Divide, and you get the final equation. Plug your numbers in. Notice that the negatives cancel, the negative from the algebra and the negative from the final velocity. So the boy gets a positive final velocity of 0.60 meters per second. Now the interesting thing to look at here is, of course, the proportionality of the whole thing. The boy has half the mass, so he has to have twice the velocity, so that 35 times 0.6 is a positive 21 kilogram meters per second, and he will have enough momentum to cancel out the man so that the final momentum is also 0. So really, we probably could have done this problem proportionally, and you did a lot of those last year with the MOPs, and if you practice them this year for extra credit, you can see some of those kinds of problems too, which if they appear on an AP test would be nice ones to get done with quickly and correctly. Second problem, we have a bullet of 10 grams moving horizontally with a speed of 400 meters per second, and we're going to assume here that it's just one-dimensional, and embeds itself into a 0.39 kilogram block of wood that is initially at rest on a frictionless table. And I want to know what the final velocity of the bullet block combo is after the collision. I don't know why the block cries, but it does. So, if the system includes the bullet and the wood, then it is an isolated closed system, so momentum must be conserved. We have the bullet, which has a mass of 0.010 kilograms, if we want to keep the units consistent, and a velocity of 400 meters per second. Multiply mass times velocity. It does have a momentum of 4.0 kilogram meters per second. The block of wood, however, has a mass of 0.39 kilograms and is not moving, and therefore has no momentum. So we can clearly see from the momentum bar graph that we have an initial momentum of 4 kilogram meters per second. And that means we must have a final momentum of 4 kilogram meters per second. But now we have the combo, which has a mass of 0.40 kilograms, 0.01 plus 0.39, and has an unknown velocity. So it must have a velocity which would give us the 4 kilogram meter per second momentum. So we could quickly figure that out, or again, we could write out the equation. In this case, the initial momentum is the momentum of the bullet. The final momentum we could look at as the sum of the momentum of the bullet plus the momentum of the wood, but it's easier to just look at it as a combo. So that way you can just say it's the total mass times the final velocity. And you don't have to distinguish the final velocities, because since the bullet is embedded in the block, it's exactly the same. Solve, plug your numbers in, and you get your answer, 10 meters per second. Plug that in. 0.4 times 10 is, of course, 4.0 kilogram meters per second, and everything works out. So I'm trying to give you several different ways of doing these problems. Some of them you can think about them proportionally. Some of them you can think about with the bar graphs, and I'll have you do a few of those. And then some of them you can deal with equations, and we'll kind of do those as well. Ideally, of course, in AP, you got to be able to write out the equations. But the others are nice to kind of get us good conceptual ways of looking at least one-dimensional conservation of momentum problems. We will, in the next few days, extend this out to multi-dimensions and inelastic and elastic collisions. Oh, one final thing here. Let's find the initial and final kinetic energies of the bullet wood block system. The initial kinetic energy would be the kinetic energy of the bullet, since it's the only thing moving, which is, of course, 1/2 the mass of the bullet times the initial speed of the bullet squared. Plug in those numbers, being careful to convert to kilograms so that we will get the proper joules out. And we get about 800 or 8.0 times 10 to the second joules of kinetic energy initially in the block wood system, or bullet wood system. Finally, the system has kinetic energy. You can calculate that kinetic energy by either summing the individual kinetic energies of the bullet and the wood block, or doing it as a combo, which I find easier. So we have to do the total mass here. Subscripts help to tell which is which. Plug the numbers in, including the 10 meters per second, which, don't forget, gets squared, that we just found in the previous problem. And we get only 20 joules of kinetic energy. So we started out with 800 joules, and we ended up with only 20 joules. So notice that while momentum was conserved, kinetic energy, not even close. And so most of the energy, 780 of the 800 joules, was actually dissipated in the process. And if you think about it, I mean, it kind of makes sense that a lot of energy would be dissipated in this collision, because the bullet gets deformed in the process, the block of wood obviously gets deformed in the process, and there would be a lot of thermal energy stored in the bullet block combo as well. And so all that deformation and thermal energy generated is going to dissipate energy, and therefore make kinetic energy not conserved. Remember, when doing these problems, you never assume kinetic energy is conserved. You never assume an elastic collision. You always assume it is at least partially inelastic. At least partially inelastic, unless you have some evidence otherwise, like you could make this calculation and show that they're both the same. Hope you enjoyed our little review.